Hello, everyone. I'm going to go over a couple of things today, and then in hopes that I will be back on Tuesday. So we're going to go over the ideal gas law sheet right now, and then I'm going to go over our new law. This is one that we got last week, and I was looking at a couple of the ones that were turned into the box last week, and I think we had a few problems with some of them. So I'm just going to real quickly go over 2 or 3 problems that you can look at and correct if you need to. So ideal gas law, this is the one that we said was real picky. I don't know if you remember that, but we said that this law is super duper picky, meaning that you've got to have very specific units. So for example, I'm going to go through and work problem. Let's work through problem number 2, because if I remember correctly, most people got the first one right because you really didn't have to change units or anything. So I'm going to present my screen, if I can do that right. Okay. And then we'll go to our smartboard, and I'm going to write some things down. But I'm looking at problem 2. I'm going to start there. And I'm going to read through the problem. And it says, what volume will 2 moles of nitrogen occupy at 720 torr at 20 degrees Celsius? Now, on a problem like this, I like to just start by making a list of all the things that I know about the problem. If I know that my volume is the thing I'm going to be looking for, I'm going to go ahead and put a question mark. Okay? And it tells me that I've got 2 moles of nitrogen. Well, if you look up there in that little box where it says we're going to be using the Pivnert law, the symbol that represents moles is which one? Which one of those letters represents moles? And it should be the N. So N is going to be 2 moles here. And it says of nitrogen. Of course, we know that nitrogen, that means we're dealing with N2, right? And it occupies at 720 torr. So if we're talking about torricellis or atmospheres or pascals, it's pressure. So 720 torr. Torr is a pressure unit, okay? And then it's at 20 degrees Celsius. Of course, Celsius is a temperature unit. So the first thing I do with my stuff is I make a list, and I do this pretty much with every problem that I do because this is what my high school math teacher told me to do when I was reading through word problems. Make a list of all the information, just get it sorted out, figure out what you've got. So now that we do, we know specifically about the ideal gas law that it's very, very picky. Okay, so I'm going to just remind myself of the units I've got to have in order to make this work. Pressure has to be in atmospheres. Volume has to be in liters. That, of course, has to be moles. R is that gas constant, 0.0821 liters, ATMs, Kelvin, mole. And this has to be in Kelvin. So it's very, very particular. So what we're going to do is we're going to, first of all, go through and just start plugging stuff in after we do conversions. We're going to have to convert some stuff first. Well, if we know that volume is what we're looking for, when we finish it, it's going to have to be in liters, right? We know that we've got moles, so that's okay. But we've got torr, and we don't want torr. We want this to be how many ATMs? How many ATMs would this be? Okay, so what we're going to do with this is we would just convert it. So we've got 720 torr. And we'll plug in a conversion factor that we know. If you look at the very back of your book, we said that there are 760 torr in 1 atmosphere. Okay? So if you set it up like that, it's going to mean that you're going to divide 720, divide your known by your conversion factor, which is 760. And if you do that, I should have got a calculator out. Get my phone here. Okay, so if I do 720 divided by 760, end up with 0.947. So 0.947 ATMs. Okay, so there's my pressure. And of course, temperature, guys, anytime you're dealing with gas laws measure movement of particles. And so temperature, you have to have the unit that measures movement, which is Kelvin. Kelvin temperatures measure movement of particles, and so we want this to be in Kelvin, so we're just going to add 273 Kelvin to it. So this is going to be 293 Kelvin. Okay, so there are all the units that we're going to need we've got everything in the right units now. So now we just go back and plug and chug. We're going to plug in our pressure, which we know is 0.947 atmospheres. So that's in the right unit. We're looking for volume. And we know the moles is 2. We know our constant, 0.0821. And then, of course, we know the temperature is in Kelvin, 293. Okay, so I'm going to go ahead and say 0.947 V is equal to whatever that is. 2 times 0.0821 times 293. I got 48.11. And then to solve for V, of course, divide both sides by 0.947. Okay, and you end up with your volume being about 50.8 liters. 50.8 liters, okay, for 2 moles of gas. All right, so there you go. And we know that this probably is a reasonable answer because normally just 1 mole of any gas at standard temperature and pressure, which standard temperature and pressure, remember, is just 1 atmosphere and like 0 degrees Celsius or 273 Kelvin. Normally that would be about 22.4 liters per 1 mole, but now we've got 2 moles of nitrogen. This makes sense. If you think about it, the answer kind of makes sense that it should be a little bit greater than 22.4 liters because you've got twice as many particles. Okay. Anyways, that's what you're going to do. That's the main idea behind all these problems. You got to check the units. This is a super picky law. Okay. So let's go and do another one real quick. Okay. So another one that you could look at if you wanted to. If you look at a problem like number 5, it says, what is the density of NH3 at 800 torr at 25 degrees Celsius? I'm going to make a list of what I know. Okay, so they're looking for density. All right, they're looking for density. And we know we're dealing with NH3, and it's at 800 torr, and that's pressure, right? And we also know that the temperature here is 25 degrees Celsius. Oops. And that's about all the numbers that they give us. And I'm just going to go ahead for kicks, say I know I'm working with ammonia, NH3, just in case I need to know anything about that. Okay, because of the fact that we've got pressure and temperature, and they're looking for density, you don't have like 2 sets of information for each thing, right? You don't have 2 volumes, you don't have 2 temperatures. So we know it's not like one of the laws that we first learned, like Avogadro or Boyle or Charles, because those were based on initial and final sets of conditions. The ideal gas law typically just has 1 set of everything. And they're saying, under these conditions, what would this gas do? How would it behave? Okay, well, this is asking specifically about density. Well, if you remember, on the ideal gas law page, we had a formula for density that was like a derivative of the ideal gas law formula. And I said it was like the dirty P law. Do you remember me making that joke? Because it's hysterical, you know, like if you're 12. So the dirty P law looks like this. We know that capital M is equal to dirt over P, dirty P, okay? So, and if you remember that capital M stands for molar mass. Capital M stands for molar mass. The D is for density, and then the rest of the letters, you know what they mean. Okay, so again, because this is ideal gas law, it's very picky. You got to check your units. So the pressure, it has to be in ATMs. So I want to know how many ATMs this is. After you do this a while, you'll know if something's in torr or if it's in, what's the other one? Torr or millimeters of mercury, mmHg. You've got to divide the number by 760. That's what we did earlier in the first problem. So I'm just going to take 800 torr divided by 760. And I'm going to end up with 1.053 atmospheres. Temperature, remember, we had 273. It's going to end up being 298 Kelvin. All right. And then because of the fact, if you look at this formula here, you're looking for density, right? And we got, so I'm going to put that we're looking for D. We know the constant, the gas law constant is 0.0821. The temperature is going to be 298 Kelvin divided by the pressure, which we said is 1.053. Okay. And now we need that M, that molar mass. Well, that's really is just what you think it is. It's where you look at the periodic table and you find the molar mass. 1 nitrogen plus 3 hydrogens is about 17 grams per mole. So we know ammonia is about 17 grams per mole. And I'm going to plug that in right there. Okay, now at this point, it comes down to, can you solve that correctly using your good old-fashioned algebra skills? Okay, so of course, we're going to multiply these two together, 17 times 1.053. I got 17.901 is equal to 0.0821 times 298 equal to 24.47 B. Okay. And then what do? We solve for D. We solve for density. Okay. So I'm going to go ahead and divide both sides by 24.47. Okay. And so I'm going to take 17.901 divided by 24.47. And I end up with the density of, I'm going to write it up here. Density of ammonia is equal to 0.732 is what I'm going to go with. And what are my units? Do you remember? What's the density units? How do we find density? Don't break my heart and forget this formula, because that's the way you're going to figure out your units. You remember density, mass over volume. So if you're dealing with mass over volume, your units for density should be grams per liter. That's what we were dealing with here. So grams per liter. Okay, that's a decimal, by the way. 0.732 grams per liter. Okay. All right. I think those were the two that I wanted to go over because, basically, if you know how to do those two, all of the rest of it is just making sure you've got the right units. You've got to make sure your volume is in liters, that you're using moles, that you're using Kelvin temperature, that you're using atmospheres instead of torr or anything else, okay? I hope you do good. So try those again. Like if you want to check your answers again from the papers in the box, you can, okay?